All right, so 2 more weeks, actually less than 2 weeks to go, right? Because I think by middle of next week we should be done, mostly. Uh, so last week, let me just remind you of what we did in 4.6. I know it's been a while. It's easy to forget these theoretical things. So in section 4.6, we saw how to compute determinants of any size n by n, but we did mostly 3 by 3, 4 by 4, and some really convenient 5 by 5 by hand. But you could do determinants either by cofactor expansion or by triangularizing it, which means you could convert it into an upper triangular or a lower triangular determinant and then multiply the numbers along the main diagonal. Okay. Word that is designed especially for this purpose, triangularizing. Okay. Again, the second one is something that you probably may not want to do unless you know the determinant is set up for that one. Otherwise, you might encounter some rough numbers. You could do it. You'll get the same answer either way. This is something that you might want to do if you know that that is what the purpose of the question was. Okay, but the cofactor expansion should work always. But apart from the computation, what we also did was invertible matrix theorem, which I wrote it once. Let me also write the opposite of what we wrote last week so that you understand clearly what this is. Okay. This is one of the key things that you should know for this week's test. That's why, and if you know this, you can save a lot of time by not doing a lot of crazy things. Okay. So if A is a n by n matrix, and suppose we know that the determinant of A is equal to 0. So last week we wrote the statements which represented a case with determinant not equal to 0. So what happens if it's equal to 0? Okay. So the following statements are equivalent, which means they are all either, if one of them is true, everything else is true. Okay. Following statements are equivalent. So statement 1, well, the determinant is equal to 0. Okay, that is one of the strong statements that would mean that the matrix is no longer invertible. Okay, so A is not invertible. So please look at what we wrote last week. Last week we had the case where the determinant was not equal to 0. Okay, that is when the matrix is invertible. This case, it's equal to 0, not invertible. Okay. Which means that the system Ax equal to B, that's a linear system. A is n by n, x is n by 1, b is n by 1. Okay. The system Ax equal to B no longer has a unique solution. Okay. Does not now all kinds of crazy things can happen. So for a non-homogeneous system, it could either be inconsistent or it could have infinitely many solutions. Okay. Infinitely many solutions, and that automatically means that there are free variables. Okay. We don't know how many free variables are there because it's an n by n matrix, maybe one free variable or 5 free variables, I don't know, but there's at least one free variable. Okay. And the same thing applies to the homogeneous system, except that it could be just the second possibility here. Statement 3, the homogeneous system Ax equal to 0 has infinitely many solutions. It cannot be inconsistent because the right hand side is equal to 0. Okay. Infinitely many solutions. And once again, that means there are, or there is, or there are free variables in the system. Okay. Number 4, the rank of A is less than n. Okay. Whether that is just 1 less than n or 2 less than n, we don't know. That depends on the matrix, but it's not going to be equal to n. Okay. And number 5, again, this could be just a small variation of what we wrote here. The RREF of A is no longer the identity matrix, okay, because it's not invertible, so you cannot reduce it to the identity matrix. We might add some more statements later this week when we do some other new concepts. Okay, but the invertible matrix theorem is probably the reason why linear algebra is such a powerful subject in math, because it has so much information to convey regarding systems of linear equations. Okay. Any questions about any of these statements about why this is true or why this is? So please compare this to what we wrote last week, okay, when we had just the opposite of all these statements. So don't confuse the two. So here's an example, okay, and understanding the invertible matrix theorem could be just answering these statements directly or using it in problems where it could be handy. So find the value or the values of k where the matrix A equal to 1, -5, 4, 2, k, 3, and 3, 1, -2 is invertible. When you get a problem like this, you should know that the idea is not to plug in all possible numbers and check one by one. Okay, that's not feasible. Okay, you cannot just start with, okay, let's start with k equal to 0, then 0.1, 0.2. Okay, that's not the idea. Based on the invertible matrix theorem, what would be a super efficient way to do this? Any thoughts about this? Feel free to unmute and give an answer. Once again, don't feel bad about getting wrong or anything. What not equal to 0? Determinant. Okay. When you say not equal to 0, the matrix cannot be equal to 0. So the determinant, okay, so set the determinant of A not equal to 0. So it is an indirect way of asking, find the determinant. Okay, so it doesn't have to explicitly say evaluate the determinant. Instead, it could be phrased like this. All right, so set that. So 3 by 3, there is nothing much going on here. Okay, so determinant of 1, -5, 4, 2, k3, and 3, 1, -2. Once again, the question is about invertibles, so the statement is not equal to 0. All right, so I'm going to expand it along the first row. Okay, feel free to use whichever row you want. So expand. Don't forget, first row has a positive, negative, positive sign convention. Okay, so it's going to be 1 times the cofactor of 1, which is, I'm just going to write multiple steps. You don't have to write all this. K3 1, -2. Then you have minus of -5, that's +5 times 2, 3, 3, -2, and then +4 times 2k, 3, 1, not equal to 0. Okay. All right, so almost there. Once you write those, set the determinant of a not equal to 0, you have kind of hit the jackpot, right? After that, it's just calculation. So this is -2k minus 3. And this is going to be -4 minus 9, which is -13. And this is 2 minus 3k. Just don't forget to multiply all these numbers here. So it's going to be -2k minus 3 minus 65. Then you have +8 minus 12k not equal to 0. All right, just finish off this inequality kind of, right? So this is 2k, this -14k minus 60 not equal to 0, or k not equal to -60 over 14 or -30 over 7. I mean, you would have never guessed that number by just staring at that matrix or trying all kinds of numbers. Okay, it's nothing special there. So you, unless you kind of use the invertible matrix theorem, you're not going to know. That is the only number you have to avoid. Okay. So as long as k is not equal to this number, you're good. All right. Any questions about why I used this particular method, or what exactly the question was asking for? Any questions? Here is another example. Okay. The determinant of a 12 by 12 matrix. I don't want to know what that matrix is, but the size of the matrix is 12 by 12. Is equal to -5. So answer the following questions. How many solutions will system AX equal to 0 have? What is the rank of this matrix? Let's call it A. What is the rank of A? Now, you shouldn't be looking around and saying, oh, I need to see this matrix to answer this. That's not the whole point. It could be a 120 by 120 matrix for all you know. Okay. So can you quickly, just look at the statements of the invertible matrix theorem and quickly give me answers to these two in just 5 seconds. Just one solution to this, and that what will be the solution? 0, right? So just one solution. It's wrong to write 12 solutions, okay? Even if there are 12 rows in it, it's just one solution, x1, x2, x3, so on x12. Okay. The question is not to find the solution. How many solutions are there? What's the rank of A? 12. That is because the whole key is that the determinant of A is not equal to 0. Okay, so it's a full rank. Of course, if that is equal to 0, I wouldn't know what it is. Okay, The rank would be 11 or 10 or 9. Infinitely many solutions if the determinant was equal to 0. Okay. So don't confuse the two cases. In this case, it is not equal to 0. You have to look at the statements we wrote last week. Okay. This is the case where the determinant is equal to 0. That's when you have infinitely many solutions. So in this case, there are no free variables. Right? Okay, so just keep that, keep the statements of the invertible matrix theorem next to you and make sure that you have copied it correctly and not the opposite way. Okay, that will be a disaster. We'll talk about this again tomorrow after we do linearly independent vectors. So it's not the last time we are doing this. Any questions about the invertible matrix theorem? Very important thing. Okay. So that is something we did what last Wednesday. The last lecture we looked at a couple of optional sections. For those of you who are not a math or physics major, probably it would have looked a little too abstract and dry, but that is how linear algebra is built up. Okay. Section 5.2, we talked about vector spaces, where the whole idea is that any mathematical object that satisfies those 9 statements that you wrote, okay, I'm not going to rewrite those 9 statements here. It has to be closed-end addition, scalar multiplication, commutative, associative, distributive, all kinds of things. And so any mathematical object that satisfies those properties 1 to 9. Okay. This was written on Thursday around this time. So they all can be kind of classified under the word vector. Okay, just like anything that flies is a bird. Okay, they don't have to look the same. Okay, so any mathematical object that has those properties 1 to 9 is a vector, which also means that right now functions and matrices and polynomials and your actual vectors are all vectors. Okay. So in an abstract sense, functions, matrices, your actual vectors in R2, R3, and so on. Okay. Those are all vectors in a set of so that's the abstraction there. Everything kind of combined into one single group. Okay. Those are vectors, and a set of these vectors which have the uniform set of properties 1 to 9 is what we call as a vector space. Okay. Once again, the word space does not mean a physical space, it just means a collection or a set of things. Okay. So I showed you a couple of examples where it could be a vector space or not a vector space, depending on all the conditions being true or maybe one of them failing. Okay. And that's where we stopped on Thursday. So let me repeat that this is an optional section. So even if you're not really motivated by all these definitions, that's okay for this course. Okay. But if you plan to stay in math and computer science or something, you probably want to do this in a stronger way. Okay. All right, so now let's move on to section 5.3, which is going to be partly optional, partly important. Okay. So we're slowly making the transition from optional to what you need to know for the semester. So the title of this is Subspace and Spanning Sets. Out of which subspace is optional, spanning sets is not optional. You might think, why are these optional things being done in this book? That's because that's the only way to sort of keep this thing, have a smooth transition from one topic to the other. Otherwise, it'll look like a very unnatural flow of topics. Before I start that, do you have any questions about anything we have talked about so far? Or any questions about what to expect on this week's test or anything? No? All right. Okay, so let's first talk about subspaces. Okay, so let capital V be vector space, which means it's a collection of vectors. Okay. Again, the word vector here at this point should mean any of those three creatures there: functions, matrices, or vectors. Okay. But at that time, you only talk about one of them. You don't mix up a matrix with a polynomial. Okay. So it's either a set of functions or a set of matrices or a set of your actual vectors. So let V be a vector space, then a set. So it's almost like the concept of a subset. Okay. So a set S in V is called a subspace of V. If the following two conditions are satisfied. Condition one, if U and V are in the set S, then U plus V is also in the set S, which means that it is closed under addition. Okay, so take any two things within that set, you shouldn't go outside of the set. So this is your general picture. Okay, this is V, this is S. If you take any two things here, add them, you should still be here. It cannot be here. It has to be inside this set S. Okay. So it's called closed under addition. And statement two, if K is a scalar, and if U is a vector in S, okay, then K times U is also in S. We don't really care about the other properties, which are more or less intuitive. Okay, so if these two are true, we are guaranteed that the set of vectors S is the subspace of V. So it's closed under scalar multiplication. All right, so again, we can write examples of this. Okay, there are examples where it is a subspace of a bigger set, or it's not a subspace. So I'll show you some examples which I did not do last time. Okay, so example one, the set of all upper triangular 2x2 matrices. It's a subspace of the set of all 2x2 matrices. You can see what I mean by V. Okay, V is the set of all 2x2 matrices. That's an infinitely big collection of 2x2 matrices. Okay, out of which I am taking a very special group. So I'm insisting that those 2x2 matrices must be upper triangular, which means it must have this form: A, B, 0, C. That's a 2x2 upper triangle. then S is a subspace of V. Why? Because if you add two upper triangular matrices, you're always going to get an upper triangular matrix. Okay. So if you take something like A, B, 0, C plus D, E, 0, F. Okay. I'm not taking any particular numbers because people could argue that it worked for some numbers, it may not work for some other numbers. Okay. So mathematicians always try to keep their proofs as general as possible. So A, B, C, D, E, F are some numbers. The only condition is that both of them must be upper triangular 2 by 2. Okay, so in this case, this is upper triangular 2 by 2. This is upper triangular 2 by 2. You add them together, and there is no doubt about this. A plus D, B plus E, 0, C plus F. That is also a 2 by 2 upper triangular matrix. And there is no restriction on those numbers A, B, C, D, E, F, because even if they are all 0, we are okay. And similarly, if you take scalar K times upper triangular matrix AB 0 C, that's going to be K times A, K times B, 0, K times C. Okay, that is still upper triangular. That is what it means by saying that this special group of matrices, which are upper triangular matrices, is a subspace of the bigger family of matrices. Okay. So I think that is probably one of the homework questions, or I could be wrong. It could be a lower triangular matrix in the homework, but it's the same idea. Okay. Let me ask you this question, just to see if you kind of get this idea. Okay. Again, let V be the set of all 2 by 2 matrices. We can assume that all the numbers inside it are real numbers. Okay, so there is no imaginary matrix at this point. And let S be the set of all 2 by 2 invertible matrices. What do you think? Is S a subspace of V? If not, you should tell me one bad example where it will fail. Okay. Can you tell me two matrices which are invertible, but when you add them together, it is not invertible? So you have to think about some freakish examples. Okay. So I'll give you one example, one matrix. You should tell me another matrix which, so this one is clearly invertible. It's 2 by 2. The determinant is 1. Okay, you cannot get an easier than that one. Can you give me a matrix B so that when you add them together, it will end up being a non-invertible matrix? Remember that a non-invertible matrix must have the determinant equal to 0, right? Yeah, all right. So one answer is 0, 1, 1, 0. So, of 0, negative 1, 1, 0. Forgot what I said there. I think probably meant this one. 0, negative 1, 1, 0. Okay. And if you add them together, you get A plus B equal to 1, negative 1, negative 1, 1. Okay. Though there are easier ways to do this, I think this is a more complicated example. A plus B is 1, negative 1, negative 1, 1. And what is the determinant of this matrix? It's going to be 1 minus 1. Okay. So you had two matrices which are invertible because the determinant of this matrix is also 1, right? But when you add them together, you get the determinant equal to 0. So A plus B is not invertible. Which means that the first condition fails, okay, that it is not closed in addition, which means that S is not a subspace. Once you get one bad example, you cannot save it anymore. Okay, you can write a million other examples where it works. The whole point is that it fails somewhere, so it's out of question. What I had in mind was this one. -1, 0, 0, -1. And then you'll get A plus B equal to 0, 0, 0, 0. But as I said, there are multiple answers possible. Okay. So that's the idea behind the homework questions for the subspace questions, which are optional, okay, but it's good to think about it, especially if you are in the math, computer science, or even physics major stream. I know it's a mixed group of students here, so it's probably not fair to impose it on everyone. Okay. All right, let's then move on to the non-optional part. So please write these definitions carefully, because if you miss a word here or there, you might end up answering opposite things. So spanning sets. So you need to take your brain out of the optional mode, not optional. Okay, so let's define this first. Okay, definition: linear combination. So let v1, v2 dot bn be a set of vectors. Even if I put arrows on top of those, they could be polynomials or matrices, so you have to kind of be adaptive to those situations. Okay. So be a set of vectors in a vector space V. At this point, you should know what a vector space is. It's a set of vectors with all those properties being true. Okay. So that is guaranteed to us that it's a vector space. And let C1, C2, C3 dot Cn be constants or scalars. Some of them could be equal to 0. Okay, in the worst possible scenario, all of them could be equal to 0, in which case there is nothing interesting. Okay. Then a linear combination of these vectors is given by C1 V1 plus C2 V2 plus C3 V3 dot plus Cn Vn. Now this shouldn't be completely new, right? So you have used this concept in differential equations when you had C1 Y1 plus C2 Y2 as a solution for homogeneous equations. So just that we are now generalizing it to a much bigger audience. Okay. So examples. Let's start with the simplest case, R2, the XY plane. Okay, so something where we can draw a picture and tell a story. So let's take the XY plane. And let's consider this vector from the point 0, 0 to the point AB. All of you at this point, I hope, knows that this is what you call as a displacement vector. Okay, so you can write this as, say, U equal to, either you can write it using the comma notation or in a column form like this. This is the same thing. Okay, so the x component is U, x component is A, y component is B here. Same thing if you write it vertically down. And I hope all of you are familiar with the two unit vectors along the x and the y axis. This is 1, 0, and this is 0, 1. What you probably might have called as the I and the j vectors in physics. Okay, those are the two vectors on the x and y axis. Then it doesn't take a lot of imagination to write the following. The vector AB can be written as A times 1, 0 plus B times 0, 1. Okay, because of the position of the numbers 1 here and here, okay, this is the vector A0 plus this is the vector 0B, and when you add them together, you're just adding two matrices, right? This is AB. What this means is that if you have these two vectors, 1, 0 and 0, 1, you could combine them using whatever constants A and B you want and generate any vector in R2. Okay, so this is any vector U. There's nothing special about A and B. Okay. So any vector U in R2 is a linear combination of 1, 0 and 0, 1. Okay, that is obvious. Okay, now that you saw it, you're like, oh yeah, that makes sense. You're just scaling the x and the y axis and just adding some constants and generating the entire xy plane. Okay, it doesn't matter what A and B are. Right? Now pay attention to the next one. This is where things get a little abstract. Okay, example 2. Suppose you have the set v equal to 1 x, x square, and x to the 3. Those are also vectors in an abstract way. Okay, these are functions of x. These are vectors because adding two functions gives a function. Scalar multiple of two functions gives a function. Okay. A linear combination of these vectors again, it doesn't matter what you call those constants. You could call it A, B, C, D, or C1, C2, C3, C4. Okay, I don't care. So A plus BX plus CX square plus DX to the 3 for some values of A, B, C, D. Okay. And some of them could be equal to 0. Who cares? Okay. At this point, I have this function which has got a linear combination of these vectors or these functions here. Now, without overcomplicating things, what name will you give for this thing which is generated by a linear combination of these four objects? What do you call this thing? From your middle school days, what is the name? Polynomial of degree 3. Okay. So a linear combination of these four things generates all degree 3 polynomials. Well, to make sure that the degree is equal to 3, you have to make sure that d is not equal to 0. Okay. If d is kind of let free, then you have to say degree less than or equal to 3 polynomials. So that is the, a lot of these things in linear algebra, once you write it down, it's not as bad as it sounds. Okay. So linear combination, wow, that sounds fancy, but all you're doing is combining things using some scalars. So that is the kind of the sub definition. Okay, we haven't defined what we really need to, because the title says spanning sets. I haven't said what that is. Okay. But to reach there, we need to know what linear combination means. All right, now let's define span. So definition. This is probably the most important definition of 5.3. And some students, they find it a little confusing, even if it's not as difficult as it looks or sounds. Okay. So let V be a vector space. Whenever I make that statement, V, it's a vector space, that means you got a collection of items to play with. Okay, that's what it means. Then, and let it be the set of vectors v1, v2, v3, dot, vn. Then the span of this set of vectors set of vectors is the set of all possible linear combinations just underline this part. It's a set of all possible linear combinations. That is what span means. Okay. And that's why I defined linear combination first, so that you know what that means. Okay. It's a set of all possible linear combinations of these vectors. So if you just take an example like this before I come back to my previous examples, okay. Examples say V equal to 1, 2, 3, 3, 4, 5, 4, 5, 6. These are three vectors in the three-dimensional space. Okay. Because it's got an x, y, and a z coordinate, x, y, and a z coordinate, x, y, and a z coordinate. So these are three vectors in R3. So when somebody says, let's take a span of V, that means you just add them, subtract them in all possible ways. Okay. So span of V and since these are kind of kind of an inconvenient set of vectors to keep on writing, let's name this as say V1, V2, and V3. Okay, that way I don't have to repeat those three vectors. So span of V will have vectors of the form this is for those of you who want a really plain language way of writing it. Okay, this is not the only list, but it's an infinite list of vectors of this form. Say V1 plus V2 plus V3, V1 minus 2V2 plus 5V3, V1 plus 1/2 V2 minus 3/7 V3. Okay. You can even just write V1 with 0 V2 and 0 V3. Okay, so there are an infinitely many possible ways of combining these vectors using some constant C1, C2, C3, and so on. Okay. So a set of all those things is what constitutes the span of those vectors. Okay. You cannot list everything because it's an infinite list. Now this is useful because now we can start communicating things in a more efficient way mathematically. So example 1, the vectors 1, 0 and 0, 1. Anytime you have a doubt about any of these linear algebra concepts, just go back to R2. Okay, this is the easiest thing you can draw and understand. This is your XY plane. Okay. These are the vectors along the x-axis, y-axis. These two vectors spans entire R2. You tell that to somebody, you will sound like a very educated person. Okay. Those two vectors spans R2. All that means is that you take any vector in R2 and you could write it as a sum or a difference of those two vectors equal to a linear combination with appropriate constants. So if you want to point, say 5, 7, it's going to be 5 times this plus 7 times that. Okay. So it's a linear combination of 1, 0 and 0, 1. There are other sets that spans R2. This is the most obvious one because of the position of the 1 and the 0. Okay. We can tweak things easily. And it's not a coincidence that those are the columns of your identity matrix. Okay. Those things are all kind of natural and connected. Can you tell me 3 vectors that spans R3? Let me see if you understand this concept. No. 3 standard vectors that will span R3. Yeah. Yep. Yep. That is the most automatic choice. Okay, there are other choices, but if somebody is asking you, got 5 seconds, tell me 3 vectors that spans R3, which is the XYZ space. Okay. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Spans the entire R3. These are the basic building blocks of that, right? And at the end of the day, it all comes down to just ones and zeros. Example 3, the set 1 x square x to the 3 spans the set of all polynomials of degree less than or equal to 3. Okay, because by combining those terms, you can generate all polynomials of degree equal to 3 or less than 3. So that's the meaning of the word span. Okay. Let me see if you understood this concept. Let me lift this up. I'm going to give you 3 matrices like this: A equal to 1, 0, 0, 0, B equal to 0, 1, 0, 0, and C equal to 0, 0, 0, 1. Hope my script plays well. What is the span of these matrices A, B, and C? In other words, if you combine them using some numbers, okay, what are you going to generate in general? When you see a question like this, put some constants in front of them and add them together. Okay. Just see what C1 times A plus C2 times B plus C3 times C looks like. Okay. That is the immediate thing you need to do. Okay. Whenever it says span, it's a linear combination, right? Write them, multiply them, add them together. What do you get? Can somebody give it a shot? Okay, nobody cares if you're wrong. Okay, that's there you go. It spans a set of all 2 by 2 upper triangular matrices because this is C1 0 0 0 plus 0 C2 0 0 plus 0 0 0 C3. Okay. One thing I've made sure is that the A21 position is always 0. Okay. So if you add this together, you get a 2 by 2 matrix with C1, C2, 0, and C3. So if you have those three matrices, it generates all 2 by 2 upper triangular matrices. Yep. So the upper triangular matrices, once again, you need to just specify the dimension of the matrix. Okay, so these are all the 2 by 2 upper triangular matrices. Okay. Any questions on the meaning of the word span? Now the next question, what kind of questions are in your homework? Okay, you should be able to do those. Your homework questions are mostly kind of uniform in terms of how it looks. So this is the conceptual part, and once you understand this, doing the homework should be easy. Okay, so for homework, which also means test number 5, so how to check if vector W is in the span of, write like this, span of set, say V1, V2, V3. I'm just going to limit it at V4, just for illustration purposes. It could be 100 more vectors. Okay, who knows? So how do we check if a vector W is in the span of these vectors? Well, if you have never seen this problem, you don't know how to even start this. Okay. So you start by setting up the equation C1V1 plus C2V2 plus C3V3 plus C4V4 equal to W. Okay, that is what it means by saying W is in the span of those 4 vectors. Okay. C1, C2, C3, C4 are the constants that could make it happen. I don't know if that is going to happen or not. Okay. I know you got tired last week with all the REFs and everything, but it's too early to put it away. Okay, we need that here. So this is now a system of linear equations. So the system of linear equations look like this. V1 would be the first column. Okay, I'm going to write like this because the vectors are going to appear column wise. Okay, so V1, V2, V3, V4. Okay, those 4 columns are the 4 vectors given in the question. It could be 3, it could be 2. Okay, that depends on the question. Times C1, C2, C3, C4 equal to the vector W. These are all vectors. You know how to solve this using Gaussian elimination. Write the augmented matrix. So that was not over in chapter 4. Okay, unfortunately, it kind of carries over into, as long as linear algebra is around, Gaussian elimination is there. Okay, so write the augmented matrix and solve for C1, C2, C3, C4. The first thing you should check is the system consistent or not? All of you answered a similar question on test number 4. Okay, you know when to expect a system to be consistent or inconsistent. You have 0 equal to non-zero situation. Okay, if the answer is no, it's end of story. Okay, you cannot go any further. Not a span. It might happen. Okay, it's not your fault. It's just the way the vectors were set up. There was something wrong about it. So if the system is inconsistent, it's not a span. If the system is consistent, then yes, it spans, and you can write a possible linear combination. That linear combination is what is going to define the span of those vectors. Okay. So you're just using your REF things from chapter 4, and most of these examples are not too lengthy. Okay, usually 1 or 2 row operations might give you the answer because the vectors are already nicely set up. Okay. So it's not as cruel as doing a 3x3 inverse or something where you have to keep on doing it, but you still have to do it. Okay. So set up the system here, write the augmented matrix, do the Gaussian elimination. If this is the case, don't worry, that's how it is. Okay. But if it is consistent, then you have to solve for C1, C2, C3, C4 and write it. All right, so that is the algorithm for span questions. Let's do a few examples. So I'm going to kind of mix it up a little bit so that you get an idea about all kinds of vectors. Okay. Just a couple of seconds here, please. All right. Example 1. Oh, that's what I want. Once again, please copy the numbers carefully, okay? Because the answer would dramatically change if you switch a number here or there. So example 1 is the vector W equal to -4, -5, 1, -9 in the span of the vectors V1 equal to 2, 3, -1, 5, and V2 equal to 1, 2, -1, 3. So the reason I'm being ultra careful in copying is to make sure that the calculations don't get ugly. Okay. Okay, so it's a standard question. I mean, maybe in another example you could have a vector V3 and V4, but the concept is the same. Okay. Once again, the question written in more layman's terms is, can you write C1 V1 plus C2 V2 equal to W for some C1 and C2? Only 2 vectors here, so that's all you need to do. Okay. Some C1, C2. In other words, is the system consistent or not? So there is a second part to this question. So if the answer is yes, write a linear combination. Usually, if that is the kind of the supplemental question, okay, that usually means the answer is yes. Okay, otherwise, there is no point in asking this. All right, it's the first example we are doing, so it may just write it kind of one step at a time. Okay, and then from the second example onwards, you could probably jump ahead a little bit. So this means you have C1 times. The first thing you have to notice here is this is written with commas here. Okay, that is a vector that kind of written column wise. So C1 times 2, 3, -1, 5. Okay, that's a vector in R4 with 4 components. So it must have 4 rows when you write it as a vector downwards. Okay. So it's not a row like this, it's a column. Plus C2 times 1, 2, negative 1, 3. Question mark, because we don't know if this is possible, okay, equal to negative 4, negative 5, 1, negative 9. All right. So it's a linear system of equations. Okay. It's a bit lopsided because you got 4 rows and only 2 columns on the left hand side. That's okay. So the augmented matrix is 2, 3, negative 1, 5 as a column. Okay. 1, 2, negative 1, 3. Augment with negative 4, negative 5, 1, negative 9. Okay. Now you have reached your comfort zone, okay, because this is something you have already done. Write your augmented matrix, do your favorite RAF operations, and identify, first of all, make sure it's consistent, then identify free variables, yada, 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 right? I'm going to just switch row 1 and row 3 and also negate it. Okay. You could do your own combinations of things. So it's R1 swap R3 and negative 1 R1. Only 2 variables here, okay, C1 and C2. Okay, so let's do R2 minus 3R1. All of you seem to be experts in doing this, so I'm not going to ask you row operations. R2 minus 2R1 and R4 minus 5 R3. R5, R4 minus 5R1. R2, 3, 4, 3, 2, 5. Yep. 1, 1, negative 1. Just keep an eye on my calculations. It's 0, negative 1, negative 2, 0, negative 1, negative 2, good, 0, negative 2, and negative 4. So that's always a sigh of relief if you're expecting a consistent system. Okay, none of those things should be conflicting. All right, so you can negate the second row, or let's do R3 minus R2, R4 minus 2R2, and then negative 1 R2. Okay, so it's 1, 1, negative 1, 0, 1, 2, 0, 0, 0, 0, 0, 0. Yes, it is consistent. 0 equal to 0 does not mean it's not consistent. It's consistent. Okay. So the last 2 equations are just obsolete because there's nothing useful going on. So C2 is 2, and C1 plus C2 is negative 1 from the first row. C1 is negative 3. So it's consistent and there is a solution. So the span is that W equal to negative 3 V1 plus 2 V2. that's the final answer. When it says write a linear combination, if the answer is yes, okay, that is what it means. So don't leave that part to me to write on a test. Okay, you have to write that thing. Usually students just say it's C1 equal 83, C2 equal 2, and then just fly away. So just write that. Okay. So as long as you can write that first step, I think you are in good shape. All right, any questions on this one? So most of the homework questions are in this flavor here. Okay, so once you get started, it's a lot of REF. Example 2, but I'm trying to do some different variety here. So example 2 is the polynomial q of x equal to x squared plus x minus 3 in the span of p1 of x. You don't have to put arrows for this. These are vectors, but not your typical vectors. Okay. P1 of x equal to negative 2x squared plus x plus 1, and P2 of x equal to negative x squared plus 5x plus 2. Is the answer to this, which question, the example 2 or example 1? The answer to example 1 is this one here. Okay, this is the final answer, because you solve for the constants and you write W as a linear combination of those two.
All right, thank you. I didn't see that.
Yeah. Now, can somebody help me kind of formulate this question? What does this mean when it says is this in the span of these two? In layman's terms, what is it asking? Can somebody just try or maybe somebody online?
Yeah, I think it would mean C1 P1 of x plus C2 P2 of x equal Q of x.
Okay, so the question is, can we write, yeah, what you said is right. So can we write C1 P1x plus C2 P2x equal to Q of x? Okay. This is the key thing that you have to get used to in linear algebra. It doesn't matter what they look like. When you say span, that means you're just asking whether that target object could be written as a linear combination of those two constituent objects. Okay, so whether they are matrices or polynomials or vectors, we don't care about that part. Okay, so can we write C1 P1 plus C2 P2 equal to Q of x? So in this case, you have to kind of go through the process of setting it up. But that's the first statement, whether it was the previous example or this example, okay, the starting part is always the same. So let's write that. So C1 times negative 2x squared plus x plus 1 plus C2 times negative x squared plus 5x plus 2. Can these two polynomials add or subtract in some way to give that polynomial Q of x? Negative x squared, no, x squared plus x minus 3. And we don't know, question mark. So to approach this in a slightly different way, you have to first expand it out, collect the coefficients. Okay, so this is going to be negative 2 C1 minus C2 times x square. Then you have plus C1 plus 5C2 times x. And then the constant terms would be plus C1 plus 2C2. And you know, we have done this multiple times. You're setting two things equal, so the corresponding coefficients must be the same. So it's equal to x square plus x minus 3. Again, we don't know if this is true. All right. So if you compare the coefficients of both sides, okay, the like terms, you'll get three equations. The coefficients of x square will give you negative 2C1 minus C2 equal to 1. The coefficients of x will give you, oops. Let me just write the other equations for the case of that. All right, so the coefficients of x will give you C1 plus 5C2 equal to 1, and C1 plus 2C2 will negative 3 is a constant. Okay. Solve it using whatever method you want. Okay, you could just set up the augmented matrix and do it that way, or you could just solve it one equation at a time. Okay, whatever is easy for you. So it's negative 2, negative 1, 1, 1, 5, 1, and 1, 2, negative 3. I've seen students who just solve it without using any fancy techniques. That also works. Because the emphasis here is not to check your REF skills, it's to see if you understand the meaning of that question. Okay, whether you can set up that equation there. Once you succeed in doing that, the rest of it is pretty routine. You can swap R1 and R2, and you get 1, 5, 1, negative 2, negative 1, 1, 1, 2, negative 3. All right, let's do R2 plus 2R1 and R3 minus R1. R2 plus 2R1 is 0. Nine, 3, and this will give you 0, negative 3, negative 4. Okay. So I think you could look at the last two rows and see that something is not right. If you divide this second row by a 9 and third row by negative 3, 1, 5, 1, 0, 1, 1/3, and 0, 1, 4/3. This itself is bad because it's telling you that on one hand you have C2 equal to 4/3. This tells you C2 equal to 1/3. Okay, that itself is bad. But if you want to So your telltale REF for inconsistent system, you could do R3 minus R2, 1, 5, 1, 0, 1, 1/3, sorry to push it this far, and 0, 0, 1. That's a sad phrase because that cannot happen. Okay. 0 equal to 1. The system is inconsistent. Okay. So the answer is no, there is no span. Okay. There is nothing else you could do about it. Any questions? It's always the first step you need to pay attention to. Yeah. Can we write that, and what does that mean for the given set of vectors? Example 3. Now I want you to look at this question and think about what this is asking. Okay. Trying to keep the examples more kind of versatile so that there is something new. Okay. Example 3. Yeah. Back to R3. Do the vectors v1 equal to 1, -1, 2, v2 equal to 3, -4, 7, and v3 equal to 2, -1, 3. Span all of R3. When a question says all of R3, that means you take any vector in R3, you should be able to write it as a linear combination of these three. Okay. I don't know, maybe it's possible, maybe it's not. Okay. So this phrase here, okay, span all of R3, means you take any vector, say XYZ, in R3, you should be able to write it as a linear combination of v1, v2, and v3. Okay. And so that's a kind of a unfair thing to expect out of 3 random vectors. Maybe they are lucky enough to give you that one, but I don't know. Okay. So how do we start this question? You have to first set an augmented system where the right-hand side is something we don't know. That's the only difference between a question where you have a clear set of vectors and a clear right-hand side and any arbitrary vector in R3. Okay. So setup is C1 V1 plus C2 V2 plus C3 V3 equal to this vector XYZ. Okay, let's call this W. Or W. You cannot say, oh, I can do it for these vectors, but not for the others. It must be for all W in R3. So the augmented system will look like this: 1, -1, 2, 3, -4, 7, and 2, -1, 3. Augment with XYZ. So my request to you now is, can you do some raw operations and see what happens out of this augmented matrix? Can you guarantee that this is always consistent for all values of XYZ, or are there some limitations? So I think it's almost there. The numbers are nicely set up. So you just need to do some convenient row operations and see what happens. Let's see what he got. So I would do R2 plus R1 and R3 minus 2R1. So that's 1, 3, 2, X, then 0, -1, 1. Of course, the augmented side looks awkward because of the XYZ. That's not a problem. You just need to write what you have. So it's Y plus X, because you're doing R2 plus R1. And R3 minus 2R1 will give you 0. One and -1. So that looks promising. And you have R3 minus 2R1 would be Z minus 2X. You know, if you disagree with anything, okay. You can add the last 2 rows and you get R3 plus R2. You can also negate the second row, but that's not exactly what we're trying to do here. So let's just keep it as 0, -1, 1, Y plus X. Add these two, you get 0, 0, 0. And the augmented side would be Z plus Y minus X. Okay. Kind of did a similar problem on test number 4. Okay. I had asked you for what value of H is the system consistent. Okay. So in this case, what do you think is the condition to be satisfied if this was to be a true statement? Got 3 letters here, that's okay. No. What is the requirement? Yep. Yeah. So that the condition is that this is a true statement. Okay. That means that those vectors will span the whole of R3 if and only if this term is equal to 0. Vectors will span all of R3 if and only if Z plus Y minus X equal to 0. If you pick your vectors so that the sum of y and z is equal to the x component, okay, then you're good. Otherwise, it's not. Okay, which means that the vectors must lie on this plane passing through the origin. Okay, if you think about this in a geometric way, it tells you that the vectors that span v1, v2, v3 must lie on the plane z plus y minus x equal to 0. That is a plane in R3 passing through the origin. Okay. If you've done some calculus 2 or 3, you probably identify this as the equation of a plane. Okay. And since the right hand side is 0, it passes through the origin. Okay. So not all vectors can lie on that plane. Okay. It has to satisfy that equation. So that is the condition for the statement to be true. Okay. So in general, it's a false statement. Okay. And the reason why it is not happening is because when you get a row full of zeros, that means you have collapsed that vectors into the same plane. Okay. So you took 3 vectors in R3, but these vectors are what we call as coplanar, okay, because they are all on the same plane. So you cannot use an arbitrary vector to write those 3 vectors to represent them. Okay. But I don't expect you to understand all the geometric meanings, so that takes time to get used to. Okay, but this is what you would do if the question is whether it spans all of R3. Okay, you have to start with a general vector like this. So useful examples for the test. So please make sure that you understand these things. Any questions on this one? One last small item in 5.3, which probably might be the easiest thing. So definition, still in 5.3. Okay, that's what we are doing and completing today. So let A be an m by n matrix. So we are back to the world of non-square matrices. The set of all vectors x such that A times x equal to the 0 vector is a subspace of Rn. And that's a detail that you probably can skip if you are not really into the theoretical part of linear algebra. It just means that it's a vector in Rn. Okay, this is a n by 1 vector, so it's got n rows. Okay. So when you say subspace of Rn means it's a vector in Rn. So it's a subspace of Rn and is called the null space of A. Again, it's a set, it's not a physical space. Okay. So it's a set of vectors such that Ax equal to 0, it's called the null space of A. Why do you think the word null is there? Any wild guess? Is the word null appropriate there? Looking at the definition, what do you think? Nobody is able to make a guess as to why it's called a null space. It's an obvious question. Yeah, because right hand side is 0. It is taking this matrix and multiplying it with a vector and giving you the 0 vector. Okay. What are we doing here? We are just solving the homogeneous system. And writing the solution in the vector form. Okay. This is exactly what we did in section 4.1 3, except that we did not use this fancy word called nullspace, but it's the same process. Okay. So solve the homogeneous system, write the solution in the vector form using the free variables. If there are no free variables, of course, the answer is 0. Okay, so there has to be some free variables to keep it an interesting problem. So this is the first of the several locations you will be seeing this AX equal to 0 in this course, okay, in different forms and different names and different shapes and varieties. But the process is the same. Take the system, write the augmented matrix, REF, identify the free variables, and so on. And since you're all experts in that, let me just do a short example. I won't drag you through the entire REF business. Okay. So example, write the vectors that span the, and span means just a linear combination. Okay. Span the null space matrix A, whose REF is (1, -1, 1, 2, 1, 1, 0, 0, 0, 1, 0, 1. Okay. And I think if you know how to do this, then you can do any bigger or smaller matrix. So it's a 2 by 6 matrix. Okay. And you can see I've already given this matrix in REF, so you don't have to do anything further unless you're really insisting on doing RREF, you don't have to do it. Okay. Two things here. Null space means you're solving a homogeneous system, X equal to 0. Okay. So there is no need to do any augmented thing here because the right hand side is 0. And when it's a span, that means you're writing it as a linear combination of vectors using the free variables. Both of which you have done in chapter 4. So as I said, this is just what do you call that? Old wine, new bottle thing. All right, so the leading ones here are in columns 1 and 4. Hope all of you agree. So x2 is free. I don't care what you call this, x2 equal to u, x3 equal to v, x5 equal to w, and x6 equal to t. Okay. I don't use the letter s because sometimes it rates as a 5, so if you like s, you can use that. So these are concepts you have to kind of carry over from chapter 4. So don't just argue that chapter 4 refers to test 4, this is chapter 5, test 5. Okay. These are still useful. So word 2 gives you, well, 0, 0, 0, x4 plus x6 equal to 0. But x6 is t, so x4 plus t equal to 0, so x4 is negative t. And the first row is the one with all kinds of annoying things. Let's just do that. Row 1 equal to x1 minus u plus v plus x4, which is minus t. Okay. U plus v, oh, minus 2t, sorry. Plus w plus t, again homogeneous system, so the right hand side is 0. So just solve for x1. We just got a whole bunch of free variables to contribute to it, so it's going to be u minus v. This is a negative t on the left side, that's going to be a right side positive t, so it's going to be plus w minus W plus T. Shift everything, change sign. Make sure that you write your answers in the vector form. So x1, x2. And please list all the variables, not just your favorite variables. Okay. Some students, they only write free variables, sometimes they only write the basic variables. Everything should be listed here. So x1, x2, x3, x4, x5, x6 equal to, let's just write it first, u minus v minus w plus t. X2 is u, x3 is v, x4 is negative t, x5 is w, and x6 is t. I'm just kind of offsetting it so that I know which columns they would appear when I separate it out. And if you got a comment on your last test for not doing the next step, please make sure that you do it in the next step religiously. Okay. Just spread it out in terms of all the free variables. That's going to be u times 1, 1, 0, 0, 0, 0 plus v times negative 1, 0, 1, 0, 0, 0. Okay. There should be 6 and only 6 rows. Okay. Plus w times negative 1, 0, 0, 0, 1, 0 plus t, which is probably the most highly represented one here, 1, 0, 0, negative 1, 0, 1. Okay, so look at the solution. It's a linear combination of these 4 vectors. Okay, so another way of saying it is that if you name this as, say, v1, v2, v3, and v4, I don't want to repeat the whole vectors. So the null space of A is the span of v1, v2, v3, and v4. Because it's a linear combination of those 4. All right, so that is end of 5.3. Do the homework, and if you have any questions, bring it to lecture tomorrow or come to my office hours. Okay. Again, you can skip the subspace part of it, focus on the span and null space parts. Tomorrow we'll do 5.4 and up to there for test number 5. Just the last one you can mess up. Okay, then. That's it. So I can stay back if you have any questions. Let me stop recording.